Okay, so in that last example, we got a the breakdown of how we come up with the shell method along with one example. So let's take a quick review of what the shell method is comprised of. So we determined that the volume of a solid of rotation using the shell method can be determined by taking the interval from A to B, where A to B are the x values over which the region is bound. Now, just to kind of preface this, we're talking about volume of a vertical axis of rotation here. This would obviously change if we went to a horizontal axis of rotation, but we'll stick with vertical for now. So A and B, those are the first things we need, are the bounds. Now, R of x is just the radius of, of the shell. And we talked about the radius being, I think we wrote this out in the last page, but I think it's probably worth writing again. The radius we define as the distance from the axis of rotation to some cross section on our region. Right. In many cases, this is, well, at least with the vertical axis of rotation, it's going to be something involving x, because it's a distance from the axis to the region on the x-axis. And then lastly, we've got h of x, and h of x represents the height of each shell. This is, sometimes it's just the distance from the x-axis up to the curve. If we've got two curves that are bounding an area, it might be the distance, the height of a cross-section between those two. So this is where drawing that cross-section, getting a sketch, is going to be particularly helpful in terms of interpreting this. So I want to make sure that we're clear of the difference between this shell method and the disk and the washer methods that we covered in 6.1. The really nice benefit here is that when we've got this vertical axis of rotation, in the disk and the washer method, everything had to be in terms of y. But in the shell method, when we have a vertical axis of rotation, everything gets to stay in x, which in most cases is going to be an easier task. A lot of folks sometimes when they see that, they'll just use the shell method for anything having to do with a vertical axis of rotation. They'll skip the washer method or the disk method, and when they see a vertical axis of rotation where things are given to us in terms of x, they leave it that way and they set up a shell method. So something to keep in mind, but you'll get some build your own intuition as you work through these problems. So to help kind of provide that contrast between, all right, well, here's a problem that we used the disk or the washer method for. Let's choose the last problem from our section 6.1 notes and redo it using the shell method instead. And I'll let you guys think about what might be the easier method. So in the 6.1 notes, we considered the region bound between y equals the square root of x, y equals x squared, and define this volume, the volume by rotating it around the y-axis. So real quickly, let's visualize that region again. So we had our first quadrant here. So we had y was equal to f of x. And if you might want to bring up your notes if you don't have them out already for this example, so we can kind of do a compare and contrast between these two setups. So we've got the curve y equals the square root of x. Looks something like this. So here's y equals square root of x, and then we've got y equals x squared right there. And this was our region. Now, looking back at 6.1, when we set this up, since we were rotating it about the y-axis, a vertical axis of rotation, we had to do a few things. We had to draw a cross section perpendicular to the axis of rotation, and then we had to turn everything into functions of y's. And that was, it took time, and sometimes it can be a little bit awkward. It wasn't too bad for this one, but in other cases it can be a little bit tricky. With the shell method, what we are going to do is we are going to take our cross section and make it parallel to the axis of rotation. I'm going to say that this occurs at some point x, and we also knew our bounds from 0 to 1 is where this region was trapped. Now here's the great news. We can leave everything in terms of x, our bounds, our functions, and then we can just proceed with our shell method. So let's see how this would pan out. So for the shell method version of this problem, we would say that our bounds are going to be from x equals 0 to x equals 1. The height, now what's the height of that cross section going to be? Well, the height is going to be that distance bound between these two curves. So it's bound on top by the square root of x and bound below by x squared. So kind of think back to finding area between curves before we started this new chapter. It's going to be the top curve minus the bottom curve on that region. And then lastly, we've got to identify the radius. And again, this radius is just the distance from the axis of rotation, right there, to our random cross-section, in this case x. So what is this distance right here? This distance from the y-axis to some point x. Well, that's just going to be x. If that was 1/2, the radius would be 1/2. If that point was 1/4, the radius would be 1/4. So the radius just becomes something as simple as the distance x. Once we have these three things, now it's just time to calculate our volume. So volume will be equal to the integral from our bounds, and that's going to be from 0 to 1, 2 pi times our radius, which is x, times our height, which is the square root of x minus x squared dx. We're going to clean this up and make it a little bit more integration friendly, so I'm going to pull the 2 pi out, and we've got the integral from 1 to 0. And if we distribute that x, we're going to get x to the power of 3/2 minus x cubed dx. If we integrate this, we're going to have 2/5 x to the power of 5/2 minus 1/4 x to the power of 4, and it's evaluated from 0 to 1, which would just give us 2 pi times 2/5 times 1 minus 1/4, and then we just subtract 0, and this should not be a big surprise. We get a volume of 3 pi over 10. Exactly what we got using the washer method in the last case. So again, I don't know. It seemed easier to me. We didn't have to do a lot of changing around, but sometimes it's nice to know that you've got a couple options.